Honors Algebra 2, Chapter 10, we're going to look at combinations and the binomial expansions. And so previously we talked about permutations, and combinations is very similar to permutations, except there's one major difference. Order does not matter for a combination. So a good example is when we play cards, like poker. When we're dealt cards, we don't care which one we get first or we get fifth in our hand. We can mix those around. So the order they're dealt to us does not matter. That makes it a combination and not a permutation. So when I'm looking at problems, I'm looking at how we have groups, and if we have n elements and we take r at a time, it's another way of thinking of how we use combinations. So you have a big group, you take some from that group, where the order you take those does not matter. It's a combination. And so the hardest part of this problem is figuring out, is it a permutation, a combination, a counting principle, how do you actually count these items? And so for a combination, it's when you have a group of items, you're taking a little bit from the group where the order does not matter. Now to evaluate that, we use the NCR as the notation, and that's n factorial divided by n minus r factorial times r factorial. So like 50c6 could be found by doing 50 factorial over 50 minus 6 factorial times 6 factorial. And like previously in our permutation lesson, we can do some reducing. 50 minus 6 factorial, we get 44 factorial times 6 factorial. And I should have put this factorial outside the quantity here. This factorial, we should have parentheses then the factorial to be mathematically correct there. So we have 50 factorial in the numerator. So this 44 factorial in the denominator reduces out with the 44 factorial in the numerator, but we still have the 45 through 50 in the numerator. And so we get 50 times 49 is 48, 47, 46, 45, all divided by 6 factorial, which is the 6, 5, 4, 3, 2, 1, multiplied together. And so then you can evaluate that. You can also plug 50c6 into the calculator. This key is under math, the TIs, and then PRB or PROB, depending on what year you have the calculator. You'll see probability, and you'll see the NCR key. And so we can also do problems with cards here. So how many 5-card poker hands are there? So we are going to do a combination because we don't care the order we get the cards. We are taking 5 cards from a deck of 52 cards. That'll be 52C5. And then you can plug it in and evaluate that to find the number of ways to get 5 cards from 52. I think it's about 2 million. So similar question here, if we're playing cards and we have 7 cards for our hand, how many ways could I have a hand consisting of 3 aces and 4 face cards? So we have 7 cards, we're going to want 3 aces and 4 face cards. We need to figure out the different groups we're looking at. And so we have an ace, which there are 4 aces, and we want 3. And then we have 12 face cards, and down here on the left it describes the different kinds of cards in the deck. If you're unfamiliar with that, the king, queen, and jack are the ones that have a face on them, so those would be considered the face cards. And so then to figure out the number of ways we can get 3 aces and 4 face cards, we would need to do 4C3 to figure out the different ways to get 3 aces from the 4. And then we're going to multiply, because of the counting principle, 12C4. So we want 4 cards from those 12 face cards. And so this is how to evaluate the number of ways to get that kind of hand. That's combinations. Make sure you really think about the different groups you have, then how many you're taking from each group, and that should help you set up these combinations. The second part of the lesson is our expansions. If we have a binomial to some degree, we can expand that. We've done that in the past, where like x plus y to the 0 is 1. X plus y to the first would be x plus y, and those have coefficients of 1. X plus y squared, we have to FOIL that. So you get 1x squared plus 2xy plus 1y squared if you FOIL that. X plus y cubed. So you have to take x plus y and multiply by x plus y squared. And so it's a lot of distributing. And you get 1x, oh shit, I got my square here. 1x cubed plus 3x squared y plus 3xy squared plus y cubed. And so you start seeing some patterns here. So I can do the next one as well. I know the pattern, so I'd have 1x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the 4th. And so we can start looking at patterns. When I look at this, I see some patterns of how the x values go from x to the 4th to x cubed to x squared to x to no x's. We also have the y's that go from no y to a y to y squared to y cubed to y to the 4th. So the first term in our binomial is decreasing. The second term is increasing by 1 each time. And we also have these coefficients here. And these coefficients, the 1, 4, 6, 4, 1, we have the 1, 3, 3, 1, the 1, 2, 1, 1, 1, 1. If I write those out here, you should start seeing a pattern. So 4, 3 and 3, 6, 3 and 1, 4, 1. This is called Pascal's triangle, this pattern here. So the next row would be, always start with a 1, add the 2 above it, and right between it, 1 plus 4 is 5, 4 plus 6 would be 10, 6 plus 4 is 10, 4 plus 1 is 5, and then 1. And that continues. Now, we name this is row 0, row 1, row 2, these are the rows. And so the rows match the degree. So row 4 would be here. So row 4 is the 1, 4, 6, 4, 1, which is 1, 4, 6, 4, 1 that we see down here. So using patterns, I can expand this pretty quick down here in the bottom. This would be row 5, which I have written down already. That would be the coefficients 1, 5, 10, 10, 5, 1. And then I can take my first term to the biggest degree 5, x to the 5th, and then work my way down, x to the 4th, x cubed, x squared, x, and then no x's. And then do that again for the y's, no y, y to the 1st, y squared, y cubed, y to the 4th. And then y to the 5th. And then we can add those terms, and that would be the expansion. So I just use the pattern to actually find that expansion. These are the patterns we've already talked about. This is the binomial theorem, which is a way of writing out that same pattern we discussed. The portion we need, though, is this. This is a formula that helps us find any term when r is equal to the term number we're talking about minus 1. N is the actual degree. And then x is the first term in the binomial, y is the second term. A few other things here. We have our NCRs, which can also be written in a parenthesis here. So these would be the same thing. So we can have like 9C2 could be written as 9.C2. And 11.4 is the same thing as 11C4. So this is just some notation stuff down here for combinations. So combinations comes back because look at our coefficients. That coefficient, the NCR, is another way of finding the coefficient within this binomial expansion. And so we can just do some examples here. If we're going to expand this, it's the 4 is our degree, so I take my Pascal's triangle and do the fourth row. Just the 0, 1, 2, 3, 4. So there's our fourth row. So 1, my first term x to the biggest degree 4, plus 4, x goes down. Our second term, 2, is going to start going up, so it's not y, it's 2 in this problem, plus 6, x squared, 2x squared, plus 4x to cubed, plus 2 to the 4th. Now we need to simplify this. It'll be x to the 4th plus, we have 4 times 2, so 8, plus 2 squared is 4 times 6 is 24. 2 cubed is 8 times 4, so that's 32x. And then 2 to the 4th is 2, 4, 8, 16. So this would be the expansion of that binomial. So this is a quick way of actually distributing binomials to high degrees. This one down here is the same thing. I'm not going to do the whole problem here, but I'm going to show you when I write this out. It's the third row. So we have like the 1, 3, 3, 1. But I want to show you this one because of what our terms are within our binomial. So this is going to be 5 to the third, and then we're going to do times 5 squared times our second term is negative 2y to the first power. This is going to be 5 to the first times negative 2y squared, and then we have negative 2y cubed. So this is 125 plus 25 times 2. So 25 times negative 2 would be negative 50 times 3 would be negative 75. And plus negative 2 squared, that squared goes to negative 2 as well. That's 4 times 5, 20. 20 times 3 would be 60. Y squared. And then we have negative 2 to the cube, so that's another negative 8y cubed. So I end up doing the problem here. But notice how the signs will alternate. You got to make sure that you take this exponent to the entire thing. That's kind of the key for that problem. So you can find a specific term, and so if we want to find the fifth term of this binomial expansion, because we're finding the fifth term, r is always 1 less than the term number, so r is going to be 4. N is the degree, which is 8. Our x value is a. Our y value is 2b. And then we just plug it into this formula. So it's going to be 8c4 x, which is really our a value here, to the 8 minus 4. And then times y, which is 2b, to the 4th power. And so you can simplify that to actually find the term. So I'm going to call it good for the night on 10-2.